Hello students, today we will discuss about comparison of charge and mass. So charge on a body can be positive, negative as well as zero. But mass of a body is a positive quantity. Charge carried by a body does not depend upon velocity of the body, but mass of the body increases with velocity. There is a relation. According to Einstein theory of relativity, m is equal to m naught upon under root 1 minus b square upon c square, where c is the velocity of light, m is the mass of body moving with velocity v, and m naught is the rest mass of the body. As we know, charge is quantized, but quantization of mass is yet to be established. We do not know about the quantization of mass. Electric charge is always conserved. Mass is not conserved, as mass can be converted into energy. Force between two charges can be positive. Sorry, force between two charges can be attractive or repulsive. But the gravitational force, as we know, is always an attractive force. Force between two charges follow inverse square law. Force between two masses also follow inverse square law. Charge cannot exist without mass, but mass can exist without charge. An accelerated charge is the source of electromagnetic radiation. It emits radiations, but accelerated mass emits no radiation. Next, we will discuss Coulomb's law. This is very important law to find the force, magnitude of force between the two charges. So according to Coulomb's law, the force between any 2 point charges which are at rest is directly proportional to the product of their charges and inversely proportional to square of distance between them. Suppose that we have two charges q1 and q2 separated by a small distance r. Now according to Coulomb's law, the force between these two charges is directly proportional to product of magnitude of these two charges and inversely proportional to square of distance between them. So when we remove this proportionality sign, we have to write here a proportionality constant K. The value of this electrostatic force constant depends upon the nature of medium separating the two charges, that is between the medium between the two charges. When the charges are situated in free space, then in CGS system the value of this K equal to 1. In SI its value is 9 into 10 raised to power 9 Newton meter square Coulomb minus 2. So we can write this K as 1 upon 4 pi epsilon naught, where epsilon naught is called electrical permittivity of free space. So the formula becomes F equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R square. In place of 1 upon 4 pi epsilon naught, you can write this value also, 9 into 10 raised to power 9. So the Coulomb law say that the force between the two charges is directly proportional to product of charges and inversely proportional to square of distance between them. But if the medium between the two charges is other than air, then the value of K is written as 1 upon 4 pi epsilon, where this epsilon is the electrical permittivity of the medium. It depends, the value depends upon the medium. It can also be termed as known as dielectric constant, relative permittivity, specific inductive capacity, or dielectric coefficient. The dielectric constant K is equal to relative electric permittivity, and it is the ratio of electric permittivity of the medium to the permittivity of free space. In vacuum, we write F as 1 upon 4 pi epsilon naught Q1 Q2 upon R square. In medium, we write it as 1 upon 4 pi epsilon. In place of epsilon permittivity of the medium, you can write epsilon equal to epsilon into epsilon R, or this can be written as F equal to 1 upon 4 pi K epsilon Q1 Q2 upon R square. The value of this epsilon is naught is 8.8542 10 is to minus 12 Coulomb square Newton minus 1 meter minus 2. When you put this value, when you will put this value at here, then this will become 9 into, approximately this is equal to 9 into 10 is to power 9. Now Coulomb's law in vector form. Suppose that we have two charges Q1 Q2, both are positive, so their product is always greater than 0. Product will be greater than 0 when either both the charges are positive or both are negative, then their product will always be greater than 0. Let they are separated by a distance r, and r12 cap is the unit vector from q1 to q2. Now this q1, both are like charges, so q1 will repel q2 along this direction, means F21 is the force on q2 due to q1. This q1 repel this q2 along this direction, so the direction of F21 is along this direction. F21 means the force on q2 due to q1. Similarly, F12 is the force experienced by q1 due to q2, because this q2 will also repel this F12. Now suppose both are negative, then again the product q1 q2 will be greater than 0. In this case also, this q2 will experience force due to q1 along this direction, F21. F21 is the force experienced by Q2 due to Q1 along this direction, and F12 is the force experienced by Q1 due to Q2 along this direction. Means Q1 will repel Q2 along this direction, and Q2 will repel Q1 along this direction. Now F12, this F12 is equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R square, and we are writing here in vector form. So this is the magnitude, this is the magnitude, this is the magnitude, and R21 cap means from 2 to 1, 2 to 1. F12 is along this direction, and R21 is also along this direction. So this R21 gives the direction of force F12. Similarly, F21 is along this direction, and the unit vector along this direction is R12 cap. We have to write here R12 cap. R12 cap is the unit vector from Q1 to Q2. Now if Q1 Q2, product of Q1 Q2 is less than 0, it will be less than 0 only when the charges are unlike. One charge is positive, another charge is negative. So their product will be less than 0. And R12, now the force between the two charges is attractive. They will attract each other. Q1 will experience force toward minus Q2. So the force will be along this direction from Q1 to Q2. Q2 will be attracted by Q1. So force will be along this direction. F21 from 2 to 1. Now F12 will be equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R square, and the unit vector along this direction is R12 cap. So R12 cap you have to write here. Here we are taking only the magnitude. And F21 is along this direction from Q2 to Q1. So unit vector from Q2 to Q1 is R21 cap. R21 cap is the unit vector. R21 cap, this is the unit vector from Q2 to Q1. Now from here we conclude that R12 cap is equal to minus R21 cap. Both are in opposite direction. This R12 is along this direction, and R21 cap will be along this direction. In all the cases, both are in opposite direction. That's why I have written here R12 cap is equal to negative of R21 cap. Now if you put the value of R12 cap, this one, add here, then this will be equal to F12 F12 is equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R square minus R21 cap. Now if we see here, this quantity is equal to F21. So it means F12 is equal to negative of F21. F12 is negative of F21. This shows that the force between the two charges obeys Newton's third law of motion. Now the cube terms of the distance means in vector form, when when you write F12 equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R square R21 cap or R12 cap. This is for when two charges are oppositely charged. So F12 is the force on Q1 due to Q2. Means Q1 will be attracted towards Q2. So force will be along this direction. And unit vector which represents the direction of this F12 is R12 cap. Means from Q1 to Q2. So for this case, I have written F12 equal to Q1 Q2 R square R12 cap. And here this R12 cap, this is a unit vector having unit magnitude, can be written as vector R12 upon magnitude of R12. When you put the value of R12 at here, you will get F12 equal to 1 upon 4 pi epsilon naught Q1 Q2 upon this. R12 is the distance between the two charges. So this can be written as 1 upon 4 pi epsilon naught q1 q2 upon this r12 equal to r. The magnitude of r12 or r21, this is always equal to r. So we can write here r. So r square into r is r cube, and this is r12. So that's why f12 is written here as 1 upon 4 pi epsilon naught q1 q2 rq r12. Here q terms appear in the denominator. This is just because of vector form. So I have told you why this r cube is written here, because we have converted a unit vector into a vector. Similarly, we can write f21 as 1 upon 4 pi epsilon naught q1 q2 rq r21 cap. Now unit of charge. Unit of charge is coulomb. So 1 coulomb is that charge which, when placed at rest in vacuum at a distance of 1 meter from an equal and similar stationary charge, repel and is repelled by it with a force of 9 into 10 raised to power 9. So this definition comes from this formula: F is equal to 9 into 10 raised to power 9 q1 q2 upon r square. So if we take r equal to 1 meter and q1 equal to q2 equal to q, and f equal to 9 into 10 raised to power 9 Newton. So if we choose distance between the two charges 1 meter and both charges are equal and force between them is this, then if we put these values at here, then q square will come out to be 1, means q equal to plus minus 1 coulomb. So this is the 1 coulomb charge. So we can now define it as 1 coulomb of charge is that charge which, when placed at rest in vacuum at a distance of 1 meter from an equal and similar stationary charge, equal and similar stationary charge should be stationary, they should be equal in magnitude, then they will repel it and is repelled by it with a force of 9 into 10 raised to power 9. Then the force between them will be 9 into 10 raised to power 9. If we take this much force, equal charges, distance 1 meter, then charge will come out to be 1 coulomb charge. In CGS system, the unit of charge is stat coulomb or electrostatic unit of charge. In CGS electrostatic, in electrostatic system, K is equal to 1. For vacuum, so we can write F equal to Q1 Q2 upon R square. This is in CGS system. If Q1 equal to Q2 equal to QR equal to 1 centimeter, force is taken 1 dyne, then charge Q will be equal to 1 stat coulomb. Electromagnetic unit of charge is equal to electrostatic unit of charge. So these are the relation between different system of units. One electromagnetic unit is equal to 3 into 10 raised to power 10 electrostatic unit of charge. One coulomb of charge equal to 3 into 10 raised to 9 stat coulomb. Now relative permittivity or dielectric constant or specific inductive capacity or dielectric coefficient. It is the ratio of permittivity of the medium to the permittivity of free space. Now there is a relation we know that F is equal to F in air or in vacuum equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R square, and F in a medium equal to 1 upon 4 pi epsilon Q1 Q2 upon R square. When we divide these two, F naught upon Fm, we will get epsilon upon epsilon naught, and this is equal to K. It means Fm equal to F naught by K. So K equal to force from here. You can find the value of K equal to F naught by Fm. Here F naught is the force in air to the force in medium. So you can also define dielectric constant as force between the two charges when they are placed in air to the force between the two charges when they are placed in a medium. Now there are two types of charge distribution: discrete charge distribution and continuous charge distribution. So when the charge is distributed over a surface such that they are separated by some distance, then distribution is called discrete. But when the charge becomes very large in number, the distance between the charges becomes very small. So they can be considered to be continuous. For example, the charge distributed over a wire, over a surface, or over a volume. So now we will discuss the continuous charge distribution. So any charge which covers a space with dimension much less than its distance away from an observation point, then it can be considered as a point charge. This is just like a point mass body. A system of closely spaced charge is said to be continuous charge distribution. It is useful to consider the density of charge distribution as we do for density of solid, liquid or gases. So for continuous charge distribution, we consider the density. So when the charge is distributed over a line, then it is called linear charge distribution, denoted by lambda. And SI unit is Coulomb per meter, because lambda is equal to charge per unit length, Q by L, when charge is distributed over a length. So unit will be Coulomb per meter. For example, this is a wire and charge is distributed over it. If we consider a small portion of this wire, then this is called small length element, and let charge distributed over it is dq, very small charge, and length is also small. So linear charge density is equal to q by L, or we can write it as dq by dl. So total charge will be equal to, when you cross multiply dq equal to lambda dl, and when you integrate both sides over whole length of this wire, then this will becomes q equal to lambda dl. Integration of dl means total charge q. Now surface charge distribution. When the charge is distributed over the surface. If the charge is distributed over a surface area, then distribution is called surface charge distribution. Its unit is Coulomb per meter square. Sigma is written as charge upon area. So Coulomb upon meter square. When the charge is distributed over the surface, let this is the surface, we consider here the small surface area of area ds, and charge over it is dq. Then surface charge density is equal to charge upon area, or we can write it as dq by ds. So total charge on the surface will be equal to cross multiply it and integrate both sides over whole surface. You will get q equal to integration of over whole surface sigma ds. This is the total charge. Now volume charge distribution. When the charge is distributed over the volume, so its unit is Coulomb per meter cube. It is denoted by rho equal to q upon v. Suppose that this is the volume and we consider here small portion of it. Charge on this portion is dq and volume is dv. So volume charge density equal to charge upon volume. This is v, the charge per unit volume. When we integrate it, you will get total charge on this volume.